In a simple two-dimensional plane, there are a lot of ways to represent each point with two numbers. One easy way that most people learn first is your good old Cartesian or rectangular coordinates. We set some point as the origin and two axes that are horizontal and vertical respectively and intersect at the origin. Then represent each point by how much in the two directions we have to go to get to the point. But as we keep going through mathematics, we come across different methods of representing points, which in some cases make graphing specific shapes way easier. Other times it allows us to make truly weird shapes. One such shape that happens in a specific coordinate system I thought of is this. What does a sine wave wrapped around a parabola look like? That sounds pretty complicated without me explaining it or visualizing it, so let's look at some systems of representing points before getting to the problem. In Cartesian coordinates, we assign a point two numbers by looking at its relationship with the origin. Specifically, for a point x, y, x represents the horizontal distance from the point to the origin. That is, the length of a straight line segment parallel to the line we set as the x-axis. Similarly, y represents the vertical distance from the point to the origin. But who says we have to use the same distance and the horizontal and vertical directions? We don't really need to stick with the same directions, nor do we need to stick with the same scale of distance. This is where the concept of linear transformations from linear algebra comes in. It generalizes rectangular coordinates to include any constant scale of distance and any direction as well. Another way to think of linear transformations is that instead of making our two main steps, the segment from the origin to 1, 0 and 0, 1, respectively, also known as the two basis vectors I hat and j hat, we instead let any two steps be our new main steps. Following this logic, the most common way to think of linear transformations is with vectors. Instead of scaling the two vectors 1, 0 and 0, 1 to get a point we want, we instead use any two vectors. In other words, we use different basis vectors. Additionally, a very useful way of visualizing linear transformations is a transformation. We can get a rectangular coordinate plane with some reference lines and do the transformation on the plane itself, or on all the vectors that each point represents. That is, the point 1, 1 on the rectangular coordinate plane will move to 1, 1 on the new plane as shown. Let's talk about polar coordinates. Instead of traditional x and y coordinates, we record two other pieces of information about every point: the distance from the origin and the angle with respect to the x-axis. The points are usually denoted as r, theta. R is often viewed as a function of theta, so theta is similar to the x-coordinate and r the y-coordinate. In this way, I like to think of polar coordinates as stretching on xy plane around a circle with radius 0, if that makes sense. Imagine a strip of the xy plane, with x being in 0, 2 pi and y being in the interval 0, infinity. If we stretch the strip so that it looks like a triangle, with the bottom side becoming a point and higher y values becoming gradually longer, we can transform this strip into a radial plane. Formally, this transformation will be f of x, y equals y cosine x, y sine x. This transformation translates rectangular to polar coordinates. Now imagine this. With that same strip of the xy plane, glue the bottom y equals 0 onto the circle x squared plus y squared equals 9, or r equals 3, and glue the rest similarly to how we did before. This transformation is sort of like translating the previous polar plane along the r-axis, where any point moves away from the origin by 3 units. Filling out the circle in the center with different values of r, the transformation we have is f of x, y equals y plus 3 cosine x, y plus 3 sine x. Now we'll go through a different way of getting to this transformation. Imagine that we get the x-axis And completely disregarding the y-axis, we mold the x-axis onto the circle x squared plus y squared equals 9. The new y-coordinate now represents the distance in the normal direction. Got that? If we get an x value, we can locate where that point would be, specifically so that the arc length from the point represented by x equals 0 and the point we want is the x value. And by getting the direction of the normal and establishing the outward direction as a positive direction, we again come to the same transformation. If we got a smaller and smaller circle to do the transformation on, we eventually get to polar coordinates, where we deal with a circle with radius 0 for mapping our x-axis, albeit that we think of the angle as our x value instead of the arc length. In summary, polar coordinates is pretty much just using a degenerate circle as the x-axis and counting the normal direction for an x value as the y-axis. This part's a bit different from what I've talked about up to this point, but it allows us to neatly tackle the problem later on. So here's what we'll be talking about. When we first learned translation for lines, you can see how the original line and its translated counterpart are parallel. But when we start translating curves, there has always been a part of me that didn't quite get that the original and the resulting curves are parallel. For example, in this exponential graph, it does kind of look parallel on the left part because it's relatively straight, but it looks like the two converge as we move to the right, even though the vertical distance between them stays the same. When the lines pass by, it almost gives some sort of a dimension to the two curves, as if it's some ribbon or a road that goes up. This is different from what I call parallel. When I see two parallel lines, the ribbon seems to be flat on the ground. If you were to create a parallel curve to another curve, then the ribbon would have to stay flat. Actually, if you think of graphing calculators like Desmos here, this flat ribbon effect is already in place. The curve itself seems to hold constant a width of a sort, and making this width larger doesn't make it look like the translated curves. To start, we can define what a width would be. Translation thinks of constant width as a constant vertical distance, but that's not what our width should be. Think about highways. If we say a highway has 8 lanes, then we should expect 8 cars lined up to fit on any part of the highway while traveling along the highway. That should be an important catch, along the highway. If the cars move diagonally on the translation example facing horizontally, then they would technically still be able to go, but the car should be facing the direction of the highway. That is, the direction we think the width is perpendicular to the direction of the highway, or the normal direction. Using derivatives, we can calculate the dimensions of the unit normal vector and add that vector to the curve we already have, allowing us to find the second curve. Visually, the flat ribbon curve already looks more parallel to the original curve rather than the translated version. We come to the climax of the video. The problem in question is not very straightforward, and I'll try to explain it. If you were to plot a sine graph onto a parabola as if the parabola is the x-axis, what would be the resulting curve? There are multiple ways to interpret what it means to consider the parabola as our x-axis. The simplest way is to borrow the horizontal and vertical aspects of x and y coordinates. For a point on the parabola, the new x value it represents would be the point's x value itself, and the new y value would simply become the vertical distance from that point. This is just a fancy way to say adding the sine wave to the parabola. The new x-axis, aka our parabola, measures horizontal distances by using the actual x-axis and counts the vertical distance as the y-coordinate. However, simply adding the sine wave leads to the result losing its sine wavy shape. This was in fact what led me to create this problem. Instead of borrowing the horizontal and vertical aspects of rectangular coordinates, I wanted to find a different way that kept more of the sine wavy shape. To focus on preserving the shape, I borrowed two different aspects of rectangular coordinates. That x-coordinates relate to the length of the x-axis, and the y-coordinates measure distances perpendicular to the x-axis. To see a simpler example, imagine plotting a sine wave on a simple line crossing the origin. The simplest way to plot it would be to just add the sine wave to the line, like we did before with the parabola. However, a much better option would be to rotate the sine wave. Both of these can in fact be expressed by a linear transformation. The rotation method is similar to what I'm going for here. The length of the new x-axis from what we set as the new origin is the new x-coordinate, and the new y-coordinate is the normal distance from the point with the x-coordinate. This is similar to polar coordinates in some ways, since the direction we take the y-coordinate depends on what the x-coordinate is. In reality, this is just a road problem in disguise, though more complex. We could simply add the sine function to our parabola, but that doesn't preserve the shape very well. Instead, we also need to take into account the normal direction at a point of the curve and the length of the curve up to that point. We set the length of the parabola from the origin to the point we choose as a function of the x value of the point, which is p of t in this case. To actually solve for this function, we have to solve an arc length integral for quadratics, which I can't do yet, bruh. Also, it's chaotic as hell, so it's probably better to just leave it as p of t for the sake of conciseness. Moving on, we then calculate the unit normal vector. The entire vector gets scaled by the value of sine of p of t. Having calculated all of this, we just add the parabola vector to the normal vector we found, completing the problem. Although the sine wave looks a bit squished near the origin because of the curvature, as we move up to the less curved parts, we can easily see that the sine wave shape is preserved, unlike the nightmare we saw before. Here's a pretty cool observation that can be made. Because the y value is preserved with respect to the normal direction of the parabola, the slope is also preserved with respect to the normal direction of the parabola. That is, if on the actual sine wave the slope is 0, then the slope of the new curve is parallel to the parabola. If the slope is 1, or the angle difference is 45 degrees on the old curve, then the difference is preserved on the new curve. And working backwards, we can use this to also define what maintaining a curve shape is. We're trying to keep the slope same while working with a different quote-unquote x-axis. Another way to see that the slope is maintained is the fact that the new quote-unquote x-axis, or the parabola in this case, is locally linear. For very small segments of the curve, we're more or less simply rotating the sine wave, maintaining the slope. Unfortunately, even though the slope is preserved, area isn't. The easiest way to show this is simply with the ribbon argument. Clearly, the ribbon on the bottom has a larger area than the top ribbon. If we were instead using area as our concept of maintaining the curve, then simply adding to the function would work. Those observations also can apply to other graphing on curves. We could get a formula with generalized functions for graphing one onto the other. If we actually go through the process of deriving the general parametric representation, we can try some pretty cool things. One idea I had was to mess around with graphing a function onto itself, like it's some boss version of that function. There's some horrendous creatures that should have never seen the light of the day, but also very cool looking things, especially with trig functions and some cute ones as well. The main takeaway I think should be the idea of extending rectangular coordinates to not only other line segments, as in linear transformations, or angles and normal directions, as in polar coordinates, but also a generic curve. We utilized a different aspect of rectangular coordinates instead of just horizontal and vertical measurements. Actually seeing the shape of the sine wave on the final sine wave on a parabola made me pretty excited, and hopefully y'all also had some thoughts on it. If you want to, there's a Desmos link below where you can plug in any two functions to graph one onto the other. Thanks so much for watching.